I always feel a little silly standing here waiting for my thumbs up from the AV guy to get started. Okay. Welcome, everybody. My name is Stephanie Malinoff. I'm the Program Director for the Roadway Safety Institute here at the University of Minnesota. Welcome to our final 11 of 11, our final seminar of 11 seminar series today. We have Professor Imran Hayi here from the University of Minnesota Duluth campus to talk a little bit about some of his connected vehicle type research. I'll give a quick intro of him real quick. For those of you in the room, if you haven't been to one of our seminars before, we do actually web stream them as well. So you'll see the video camera in the back. If you have questions, we'll save them to the end, but I will ask that you use the microphone so that folks who are watching remotely can hear our questions as well. For those of you that are signed in online and watching the seminar, there should be a chat bubble in the upper right-hand corner of your screen. If you could click on that and sign in, let us know your name, your organization, and how many people are viewing the webinar from your location. That information would be greatly appreciated on our end. That's also the area where you would be able to type a question if you have one, as Professor Hayi is giving his presentation, that we'll read them here on site in Minnesota after the presentation. For those of you who are students enrolled in the course, see Kylie at the end. Kylie, do you have any papers to hand back today? A couple of them. So if you need anything from Kylie, she's in the back. She also will be able to give you any updates about final grades and all of that information when you can expect to see those. Professor Donath was not able to be here today. He may have landed already, but he's in flight to Washington, D.C. for some meetings this afternoon, so sends his apologies. So with that, let me introduce Professor Hayi. Again, he's from the University of Minnesota Duluth campus, and he works in the electrical engineering department. And he's here today to talk to us about some work he's been doing. The title of his presentation, Improving Traffic Safety and Mobility Using DSRC-Based V2V Communication. I hope that matches what was on his screen up here. With that, please help me welcome Dr. Hayi.
Thank you very much, Stephanie, for the kind introduction. And Kylie, could I know that how many students are on webcast? How many? Are there any people? Can we see if there are any people?
Remotely?
Yeah, remotely. Just to see whether I need to focus just on these people, or if there is anybody there as well. Okay, just one. All right. So I think what I really mean is that I don't have to wait until the end for the answering the questions. If you have any question in between, please raise your hand. It's better to clarify the question at that time. Otherwise, I don't feel like speaking continuously without satisfying you. Here, what I will do is I will describe this work which we have been doing at UMD related to DSRC, vehicle-to-vehicle communication, regarding development of information system, traffic information system. So we went through various phases since last 3 or 4 years of work, which I'll try to summarize here, only regarding the information system development. We are doing a couple of other things too related to DSRC, which I will not talk about on this, but if you're interested, there is Connected Vehicles Research Lab we have developed, and if you Google it, CVRL, Connected Vehicles Research Lab, and you can find some more details about our projects there as well. So first, what is connected vehicles technology? It's that vehicles can talk to each other, just like human beings can talk to each other using cell phones. If there is a built-in cell phone within each vehicle, they will be able to talk to each other. I hope that they won't do too much social timing. They do more objective-oriented tasks. That's what the purpose is, and that's really the safety, mobility, and efficiency, right? That objectivity will increase safety, mobility, and efficiency of the traffic scenario. And if happens, I sometimes joke around that if they follow human beings, what we do when we are able to, we have ability to talk to each other, then I think we will rather go in reverse direction, not improving them, rather decreasing that. So how does this really work? I'll give you a brief introduction of DSRC technology overview, very brief, then some of the applications, and then work zone environment specifically I'll mention, because the information system, traffic information system, which we have developed over the last 3-4 years, we kept in mind the work zone scenario. but it is also, you will notice later on, it is also applicable to other regular scenarios, rush hour scenarios, or where if an accident happens somewhere. But specifically, we had the work zone in our mind when we developed that. And then the first phase was V2I traffic information system, vehicle to infrastructure. And then the next stage was V2V-Assisted V2I system. And then I'll mention about that. And then variable message sign integration, the hybrid of the, there are many variable message signs. How do we integrate that? My fault. How do we integrate that in our system? And then at the end, just the V2V part. We will just get rid of the I part, means any roadside unit we will get rid of. And that's our current work. We just did a field demo, a small scale field demo on this. So this is still a little bit of going on in the finished phases, but basically this doesn't depend upon any roadside infrastructure. And then of course I'll leave some time for question answers as well. So first, the DSRC technology overview. It's a shortwave, short to medium range communication. 5.9 gigahertz is the central frequency, and the range is about 1,000 meters, 1 kilometer, theoretically. But practically, we have not been able to achieve more than 500 meters. And considering the road curvatures and in between, vehicle to vehicle, not all vehicles have it, some vehicles can come in between, line of sight is blocked, then it is even crippled. So we have to consider in mind, especially when you have to hop the message from vehicle to vehicle, you have to see, that the range is about 200 to 300 meter practical range. So this is important. The data rate is small, but it's good enough, cars can enjoy objective communication with each other. There are 7 licensed channels. There are a couple of them which are reserved for the basic safety messages, the high priority messages, and the other ones for other kind of messages, some apps which are not essential. If you look at the iPhone, for example, right, the phone, the message, Safari, these are essential built-in apps, right? These are high priority, but any other apps or the other applications, for example, you can consider the information system which we are developing is kind of apps for those devices. And if all vehicles have those apps, this information system will work more efficiently. And of course, the advantage is that the vehicle speeds could be very high, 100 miles per hour, and it still works. So some of the potential applications of DSRC, I have a list, and there could be more as well. Traffic information systems, emergency vehicles, signal preemption, and many people are working on some of these applications. I think this is very, very similar in both of them. The weather and road conditions alert systems, curve speed warning, do not pass warning, cooperative adaptive cruise control, and cooperative forward collision warning as well. So left turn assist, merge assist. Now we are also working on some of the merge assist. We have done some work on the signal preemption also, emergency vehicle, but mainly I'll be talking about this traffic information system here. The development through last 4 years at least. So the information system, the traffic information system, we designed initially for the work zone environment. And you can see the work zone. I'm sure you will all have experienced this work zone, especially in summertime, not necessarily in winter time, in Minnesota area, but other parts of the country in winter time as well. So if the work is going on, usually 1 or 2 lanes are blocked, and usually you have just 1 or sometimes 2 lanes open. And of course, especially rush time, the cars starting to build up, the congestion starts to build up, and what happens? The delay, right? The travel time increases, as well as the start of the congestion actually is a variable, right? Usually the end of the congestion is fixed, but start of the congestion can grow. As congestion grows, that parameter varies, and we will be able to estimate both travel time as well as the start of the congestion. Now I'll mention about that, but first, why is really the problem? Although you can see that in the last few years, the number of deaths and accidents, have reduced on work zones, or work zone related accidents and deaths. But I think 2 weeks ago probably there was a towards zero deaths conference in Duluth. That is the real goal. you want to make it 0. So how do you do that? Of course, many other things will be done, but this DSRC technology seems to be promising to achieve, to contribute towards that to some extent. So first now I will mention this V2I traffic information system. This is what we did 4 years ago, but 3 years ago we kind of demonstrated it. And I'll mention first the architecture and design, and then we also did a field demonstration, which I'll talk about. And these are my students who have worked hard with me over the last few years. Some of them are still with me. So the fundamental architecture works this way. So you can see this is a road, and suppose this 2-lane road, both going this way, and these are coming this way. So one lane is blocked, and then the traffic is only routed now through this lane. And if there are more cars, congestion can build up. Now what happens is, of course, few cars, as the market penetration grow, not every car will have DSRC units. So we are assuming few cars have DSRC units. So if we put a roadside DSRC unit, and we call it portable unit because only one roadside unit is needed, and you can take it to any work zone location, or even if an accident happens and you have to close some lanes, you could take it there as well. So it's a portable roadside unit which will exchange some dialogue and will pick one vehicle which is just outside of the start of the congestion area. And how that is find out outside? Because the speed has to be the free flow speed, and we will assume that the free flow speed is the normal speed limit, around the speed limit range, and this DSRC will need to be programmed of these parameters, the speed limit, etc., and also the road width, which is needed for some detailed calculations, which I won't be able to mention all those calculations, but basically this will be programmed with some initial information which will be needed to make some calculations. So it will pick a car, and then once this is picked, then this will keep on notifying this while it passes through the congestion. So when it crosses the congestion, it will ramp up, the speed will go up again, and then it will know when the speed goes down and speed comes up again, what is the travel time between that. And when the speed goes down, it has also the long lat, the coordinates of that point, and similarly of this point, end of location, which is known. So this will be able to know what is the congestion length. So that's how this DSRC unit, which is a roadside unit, will be able to know what is the congestion length and travel time. And then it is also in parallel, it is acquiring these parameters, but in parallel, periodically, every second or every few seconds, it is transmitting those parameters in a form of information message, and which message could be communicated to the vehicles which are yet to approach the congestion. So they will be able to know what is the travel time ahead of me and where is the start of the congestion. So once we did the demo, we chose this Rice Lake Road near UMD campus in Duluth, and you can see this is the RSU. And if I go back, I want to mention this, that the range is about, theoretical range is about 1,000 kilometers, practical maybe 500 kilometers. So you can only assume this is about half a kilometer distance and half a kilometer distance, right? And of course, this is not practical distance. You're thinking about, oh, how it's going to help, right? We're going to talk about that later on. But this is symmetric. You want to make sure that you cover the end of the congestion location with this roadside unit. So this leaves about half a kilometer here and half a kilometer here, or maybe if you're lucky, more. So, but here you see during the demonstration we use asymmetric, right? We had the RSU close to the end of the congestion here. Why? Because we had our car, ideally when DSRC is built in, the antenna will be at the top of the car and there won't be any obstruction, but we put the DSRC unit on the dashboard of the car, and when we were going this direction, RSU was able to see through the windscreen that antenna. So the range was more. But when we crossed this RSU, the back of the car obstructed, the antenna. So the range was crippled on that. That's why we had to do this asymmetric demonstration. So, but anyway, we were able to come here in a car. This is actually one lane this side, one lane this side, but there's a vast shoulder. So what we did was we drove the car on the shoulder to simulate congestion. And that's how, we took many rounds, and each time, these are some of the results. You can see that, the car, the speed came down, and then this is the distance, and then the speed came up after that. So this is the congestion length, and this is the travel time, same versus time, right? So this is the travel time. But the problem with this is, as you're already thinking, what this is like few, half a kilometer or so, that's not practical, right? Have you seen a work zone where, the congestion length is such a small, and if the travel time is this much, that's not a problem, right? We're talking about travel time 30 minutes, 40 minutes, sometimes 60 minutes through 1 mile or 2 mile long work zones. That is the real problem, right? So how to solve that? So this was the first phase, and then later on we realized, and by the way, these are some more results. We repeated the experiment many times. We wanted to make sure our system is robust, and we varied the congestion length as well as depth of the congestion. So every time it was successful, but again the same problem. The distance is small. So how to solve that problem? And then we came up with V2V-Assisted V2I, and I'll mention why do we call it V2V-Assisted V2I. Here the same thing, the roadside unit, but you can see this is more practical, congestion length and work zone. It could be a couple of miles, but the DSRC won't be able to communicate directly to the vehicles here, right? And we want to pick a vehicle here before the congestion so that it can actually complete that whole profile, the speed going down and then speed coming up again. So how to do that? So we thought that this can talk to these vehicles through V2V, right? So this can send a message which can be hopped, and then this can send a message back, and which can be hopped, and it can be reached to the roadside units. And that's what we call V2V-Assisted V2I, because we still use this roadside unit. And you can see this is what I was talking about, right? Using the hopping mechanism. And doing that way, you could cover the congestion lengths about maybe a couple of miles or 2 to 5 miles, but also another advantage that you can hop the information message to 5 to 10 miles away from the congestion. So the vehicles can really know well before hitting the congestion, that if we have an alternative route to take, we can, to make some well-informed decisions. So that would be really practical. This is what we thought, and to accomplish that, of course, important thing is that we had to come up with this mechanism of selective relay and directive relay. What is that? I'll mention, but mainly, you want to send the message, and the message is hopped here. You can see these are selective vehicles which are hopping, and also in this direction only, right? There could be some crossing roads as well. So we want to make sure that the message is not hopped by every vehicle, right? Whomever receives it. So if that is the case, then it will be a message broadcast, bandwidth storm kind of situation, and that's what we wanted to avoid. So we came up with these two algorithms. One is selective relay. What we thought was that this is RSU, right? It will be transmitting in all directions, and it could be an OBU2. It will be transmitting in all directions. So all vehicles will receive it, which are around it. But we want only that vehicle which is the farthest from the transmission origin to hop. And that's why we are picking this, right? So we split that into bands, and then this vehicle, all these vehicles will, after receiving the message, will wait for a random period of time. Random period will be picked from a window, and the window, this will be the shortest. So the random wait time will be the shortest. So this will broadcast, and then when these will receive it again, the same message, they will cease to broadcast, so they will not broadcast again. So that is basically selective relay, and this way we can maximize the number of hops. And if unfortunately if there is no vehicle here in this band, then this will be able to transmit. If there is no vehicle, this will be able to transmit. So at least we will ensure that whichever vehicle is present, it will be able to transmit the message. And then directive relay, what we really mean is that we want to make sure that the message really goes here. You can see this message will be received by this vehicle as well as this vehicle. From here, right? From here. So this is the band, the longest distance band, shortest wait time. So this and these two vehicles will receive it. We don't want this to transmit because the problem is on this road. We don't want to mislead this vehicles on this road. So what we will do is there is always a natural curvature of the road which we will measure, and we will compare, say, this angle with the previous hop, right? So this angle has to be comparable. But if you compare with this angle with that angle, they are quite different. So it means you are not on that road. So the natural curvature. We did some civil engineering studies. I don't know if somebody is from civil engineering here. I learned quite a bit of civil engineering, how the road curvatures are designed depending upon the speed limit, and so that's how we came up with some of the numbers, some of the limits which we don't have to cross to pass this test before we can hop the message. So these are the two things which we came up with, and we implemented this algorithm, and now you can see the same location. We demonstrated this. This is now our RSU, and you can see the congestion is much longer, and RSU can only cover directly here. And we had by that time about 5 OBUs, and one OBU we used OBU as an RSU, and then the remaining 4 here, and we try to synchronize, of course, their intermediate distance, so that we want to make sure that this is not outside of the range, right? So that's how we were able to demonstrate that. And you can see this is just the sample of the vehicle which we used, and that's what I was talking about. We placed the DSRC unit here in all cars, and then you can see the back of the car can actually cripple the range towards backwards. And you can see now the distances are longer, right? Although still not practical here, because this was the limitation of the number of devices which we had at that time. We had only 5 devices, but if we had more devices, we can demonstrate it. This theoretically, this is scalable. This can be demonstrated for longer distances. As a matter of fact, as of now, we are working not under Roadside Institute, but I'm working with Savari Networks, who are manufacturing some of these devices which we use on a US DOT funded project to demonstrate this in-vehicle message transmission using hopping algorithms. And as a matter of fact, this next summer we will be doing much extensive tests. And once we do that in Duluth, we'll be doing the same tests in Virginia with VDOT, because that is what their requirement is, that we actually do it ultimately there as well. So this is the time. So these were our results. But now the next step is why VMS. We needed to think about VMS integration within our system, and I'll mention what does that mean. So market penetration is, again, everybody. You can even still now think that people think, oh, when will we have it, right? It may be, some people think it may be 5 years, some people think, oh, maybe 50 years, right? This is really a lot of range in between, people who think that when they will have DSRC in their car. And we know that also once even everybody is really committed, the market penetration is going to grow slowly, right? First few cars will have it, and then more and more and more. So how many cars, we want to analyze how many cars are needed to acquire these travel parameters. So this is the first problem, right? So we did some study how many vehicles are actually needed to acquire these travel parameters, and we did again some civil engineering stuff. In free flow situation, the Poisson distribution, right? The headway are the vehicles count crossing a certain point, right? Both are Poisson distribution, but if this is kind of a congested flow, it could be a uniform distribution between the cars. So we did that, and these are some of the basics of civil engineering. Civil engineering students might be very familiar with these basics. So we used this and came up with this these statistics. And the first thing was that we wanted to see that the vehicle, right, which we want to pick before the congestion, they should be, we don't want to wait forever before we get a DSRC. We pick a DSRC equipped vehicle, right? So that will help us measure the travel time as well as the congestion length. We did not want to wait forever. So if the travel time is 15 minutes or to half an hour range, we thought, a small fraction of that, about 30 seconds or so, right, less than a minute time, we should wait. If more than that means a system is not that efficient. So that was our criteria. So how many, depending upon the vehicle flow, we can figure out, how long we have to wait before we pick another a DSRC equipped vehicle in 30 seconds. So I think this is the average time between two DSRC equipped vehicles for a given market penetration, right? Versus the vehicle flow. And we came up with this, and these are the calculations which we will use to show what is the market penetration needed for our system to work. Not only this, but also another thing, that we want to make sure that the message can be hopped, right? If the two vehicles, if the market penetration rate is low, if the distance between two DSRC equipped vehicles is too longer than the range of the vehicle, then the hopping will stop. So we did not want to do that either. So that really depends upon the density, traffic flow density, right? But both are related. Flow and density are related, so that complicates the situation. But this is versus traffic flow density and average distance between the two DSRC equipped vehicles for a given market penetration rate, right? So we had these numbers now, which we could use, and we actually got some real data on I-694 here. On both lanes, and this is the traffic flow, and this was a typical one-day data, both rush hours and non-rush hours. And considering that, we came up with, using those previous plots, we came up with this, by the way. The DSRC market penetration, what is the flow, the vehicle flow needed, and what is the vehicle density needed, right? So as the market penetration increases, the requirements comes down, obviously. But we noticed that, that in the rush hour, market penetration need was only 20%. Why? Because more cars, obviously, right? So, and non-rush hours about 35% for this system to work. So this is the data which we were able to come. That was a good news in a sense, but bad news that, how to communicate this data to everybody. That was the real problem. You can acquire with a small percentage of, DSRC market penetration, but everybody needs to benefit, otherwise it's useless, right? If not everybody is able to see what is the travel time ahead. So to solve that problem, we came up with this idea of this VMS integration in our system. So we thought that this DSRC, we will equip these VMSs with a DSRC unit, and they could act as a car, right? When the message is being hopped, they could get a copy of the fresh information message. And with the fresh TT, travel time, as well as this, the start of the congestion location. And then it can calculate the distance, right, for the start of the congestion location is here, and it can calculate its distance from there and can display that congestion had maybe 10 miles, right, or 7 miles, or 2 miles. And similarly, the travel time ahead will be so many minutes, right? So this is useful for those cars which are not equipped with DSRC units. So I think that's how we came up with this idea, and that's how we started working, that how do we interface DSRC unit with the existing VMS. And we were lucky that MnDOT, they were able to loan us one of their PCMS, they call it, programmable changeable message sign as well, in addition to VMS. So we were able to work with that, and then this one is that controller of that PCMS which we got. This was that kind of PCMS which we got. It's made by ADCO, and we communicated using this serial port, right? This doesn't have to the wireless connection. This is part of the PCMS or VMS unit. And we had to learn the programming part, of course, this interface which was serial port, and then the programming, how to program it and it works, and how to translate that the DSRC message to basically in its language. My student actually worked many hours in the garage there, the big garage. It was a heated garage, so even he worked in winter time. So I think this is the kind of video, if it runs, I will show you that we were able to make it work, and you can see the travel time, right, 36 miles, and caution work zone ahead, and this is one, and the other one was travel time and then queue head, right, the start of the congestion. So we would switch, if the two PCMS is not available, we could switch between the two. So these were the two important parameters which we came up with. So that's how we were able to successfully demonstrate that with the VMS it can be made useful with lower market penetration of DSRC as well. And this is my student actually. This is the heated garage. That's where he spent a lot of his time 2 years ago. And now the last thing, the V2V system. This is actually some of the work which is ongoing, almost done. We're just wrapping it up. I don't have slides related to that, but I'll mention because I think I look like we still have some time, so I'll be able to mention some of that. But before that, before leading to that, let me just mention what in stages, summarize so that you know why we need this. So this is the current work, right? I'm leading towards current work will come here. But this is something which we did the first time, right? The RSU, and this is about half a kilometer or so, right? So this was our first step, and we are able to design the V2I system. And then V2V-Assisted V2I, because we thought, that's not practical. To make it practical, we have to make sure that we cover the practical lengths of work zones. And this is the V2V-Assisted V2I, right? And then we had to integrate VMS, DSRC-equipped VMS in it, so that, although small percentage of DSRC-equipped vehicles were needed to acquire traffic parameters, but to disseminate to everybody, we needed this. So we did this. So it's actually it is still V2V-Assisted V2I system, but VMS integration. This is not right, but it will become right because that's what we are doing now, right? We want to get rid of that. So if you get rid of that, why you need to get rid of that? Because it's a roadside infrastructure, one device. The whole system will depend upon this. If something happens to it, human error can happen, in programming and inputting some of the parameters. So the whole system will fail. So you don't want to do that. So we want to make sure that if we can make it independent of that. To make it independent, the first thing which you can imagine that, how to pick this vehicle, which is outside of the congestion. How do we know? So we have to again revert to some of the, traffic flow engineering that when you hit a congestion, what usually happens, right? What happens? You see something, right? In the nighttime, maybe the red lights, or even the daytime, right? And then you start braking, right? So that we want to use as a trigger to pick a vehicle from the road. So we'll call it ad hoc host. So once we pick an ad hoc host, that will basically go the same way. We'll calculate the travel time and congestion length, and it will also, the ad hoc host will do the same job as this was doing. It will not only acquire those parameters, but also will disseminate periodically, and those messages will be hopped the same way, right? And so that was the only additional thing which we want to do here. And you can see that right, so the congestion, basically this is the same system we want to show, but so we want to pick this congestion. But how do you really pick when the vehicles will undergo that threshold of braking? Then they will issue a trigger message, and that trigger message, we should not say that randomly. Okay, any person can sometimes randomly brake and can see something. We want to avoid that. So multiple vehicles will undergo that trigger, and then they will under that braking profile, and then they will issue the trigger. And then the trigger will be received by the vehicles which are further behind, a little further behind, and then they will be able to see, okay, now there is congestion ahead, and then we will pick one vehicle from these vehicles which have received at least 2 triggers, and so that this vehicle is still in free flow, and then it will be able to undergo that speed reduction and then speed up again. So that way, this will be the congestion length, this will be the start of the congestion location, right, in terms of long lat coordinates. So that's how we want to make it work. But considering to pick up that threshold, what should be that threshold to issue that trigger? Now we came up with this, and we just learned this. This is well documented in civil and traffic flow engineering literature. And this is the standard braking profile. This is the cautious braking profile. Means if some drivers are really cautious, they brake well ahead of time, right? So this is the problem, but they brake well ahead of time. Some are really, emergency brakers, right? They won't brake until they have to, 11th hour, right? So that is the deceleration. So very high deceleration, reasonable deceleration. This is the standard deceleration, and actually I think the 85 or 90% of the people undergo basically this kind of deceleration when they see some some object on the road in front of them when they have to stop. So this is about 3.4 meter per second square deceleration, and I think that's what we chose as a threshold. And you can see, this is the kind of scenario that this is the standard deceleration, and this is the emergency, right? So somewhere in between you will be, and this is a typical trajectory of a vehicle, right? So when you go down, and that's how this will happen. And as long as after 1 or 2, right, deceleration, then deceleration may end, right? If you depending upon what is your deceleration in the first brake when you hit the brakes, and then the speed has to be lower than this limit. So there's some detailed calculations involved, and if somebody is really interested, I can discuss that. What are the rationale behind these parameters? But as long as you are under this light blue area, we will make sure that this is the reasonable trigger, and you can actually pick a vehicle ad hoc host based upon these triggers. And there are some other things involved too in this. Road can be curved as well at that time, so how to really see that how far you are, and there could be a parallel road and a crossing road. We want to get rid of that, so we came up with a more elaborated protocol to make sure that we don't pick the wrong vehicle at wrong road. So by doing that, this is actually very crude demonstration. It's not a full-fledged demonstration, and you can see these are the 2 vehicles, right? This is the congestion, same location, 2 vehicles, and these are the 2 vehicles. These 2 and we maintain the distance between these 2 vehicles and these 2 vehicles about 200 to 300 meters, so that these vehicles will undergo the braking profile. They will issue the trigger, and then both of these vehicles will get the trigger, but I think based upon some, again, contention resolution algorithm, we will pick one of them as the ad hoc host. So that's what we demonstrated. This is very crude demonstration just for the ad hoc host selection part of it, because other parts technically we have demonstrated before. So in a sense, this system is ready, but now the 2 problems which we are working now, and they are also been solved. If we get rid of that roadside unit, right? Before, what happened was, when the roadside unit used to transmit the information message that this is the travel time and this is the start of the congestion location, you could also program that this is the road, say I-35, right, or I-694, that this is the road where the travel time is this and the congestion is at this landmark. But now we are done, right? We don't have that information. The vehicle could be anywhere on the road, and it could be triggered. Okay, now is the ad hoc host is chosen, right? Trigger and then ad hoc host chosen. So how do we know the message is going backward now? Now the crossing roads or parallel roads can receive that message too, and they can think, it's so long ahead is travel time this much and congestion, it may be in our road, right? So we want to avoid that. So how do we do that? First thing is that we want to make sure that we have that kind of a navigation system, right? The GIS data, the mapping data in our DSRC box, so that once we know this is the start of the congestion, right, or long lat coordinate, you will be able to know which road you are on, so that can be displayed to the driver, right? So we interface that GIS data into it. And one of my students, she just graduated, and she actually worked with GIS with our geography department, got the GIS data, and then interface with the DSRC box and develop that algorithm. And I don't have those slides with me, but the algorithm is based upon, we want to minimize the calculations. I do not know how to the navigation. Of course, the navigation devices do, but this is similar. It's nothing new, but we came up with our own algorithms. It's very difficult for, from my experience, to work with those navigation devices companies, because a lot of information is proprietary. But we came up with our algorithm, and we did demonstrate that, and it works great. We moved around in Duluth. I had my student with me, and we moved around, and I was testing her. And we moved around, and every time I made a turn, and then the computer said, okay, we are now on this road, through the DSRC devices, through the DSRC device processing. Nothing was done on the computer. The computer was only for the display part. So we were able to do that. And then the second problem, second problem is that now that is also present in the V2I-based system as well. That what about if the travel time is half an hour, 30 minutes, right? we will not be able to update the travel time unless an ad hoc host or a vehicle which is picked, it will cross the 30 minutes, right? Maybe it is in the middle of the travel time that the congestion has grown even further, right? Especially rush hour. So we are giving this delayed parameter. If we want to update that new travel time and new sort of the congestion location more frequently, we cannot do that. We were stuck with one host or one ad hoc host, right? One ad hoc host in V2V-based system and one host in V2I-based V2V-assisted system. So to avoid that, we want to make sure that we pick multiple ad hoc hosts, right? Multiple ad hoc hosts, so that, you know, maybe every 5 minutes or whatever the desired update frequency is, maybe every minute. It will be too complicated, of course. You know, you will have many hosts, but we came up with this algorithm. Actually, one of my students who is graduating, who is defending this this January 9th is his defense date. He came up with this multiple ad hoc host mechanism. You know, he developed the algorithm, and we did not test in the field because it requires many vehicles to have DSRC units, and a lot of synchronization is needed, so we were not able to do that in the field. But in the lab, he did that. He came up with this method that, you know, he drove these vehicles, DSRC equipped vehicle with GPS on a road, and simulated various congestion. If I go back, simulated various, you know, these practical, you know, going down and coming up, right? So he had many of them, and then he used them in the lab, and each, you know, he basically, instead of in the lab DSRC device, instead of getting the actual GPS data, it was picking from one of these files. So we were simulating that those devices are actually on the road, right? So that's all. The GPS is the only difference. Otherwise, they could communicate with each other, and then using that, actually, he demonstrated that his algorithm is working well. And I don't have those slides, unfortunately, with me, so I won't be able to show you that, but that's what we just did. So these are the two main problems which with the V2V-based system, and we try to solve that, and that's it. So that's why I took more time on that. So I wanted to get you some information on that. I think that's about it. If you have no question, I wanted to leave about 15 minutes for the questions. If you have any questions, I'll be able to entertain those.
If folks have questions, just raise your hand. We'll bring the microphone around so the folks watching remotely can hear as well.
So,
it won't project in the room.
so how did you get those? I'm talking about V2V system, where you, how did you sense the red light of the vehicles?
Okay. Yeah, we did not sense the red light. You know, I was only using the analogy that when you see red light, you brake. So I think this is automatic. The vehicle, let me just see, maybe here, right? So each vehicle will be actually acquiring GPS every second, for example, right? Every second. Now actually the GPSs can acquire every 10th of a second as well. So every second it is acquiring a GPS unit. It's calculating its speed as well as deceleration, right? So as soon as the deceleration is below a certain threshold, which was below a certain threshold, which was 3.4 meter per second square, right? Or minus 3.4 meter per second square, then it means there is a problem, right? So there is a problem. So that's one indicator. But it means if this can happen, you know, randomly, if this is below, goes down, and then suddenly you come up again, so we will ignore that. But if it comes down and stay close, right? Stay down, and the speed also becomes less than the free flow speed, then that is the criteria which we use.
So this means that vehicle should have that equipment in it, right?
Should have equipment, as well as, you know, that program should be running so that it can actually detect that there is a congestion and my speed is reducing. So it's a speed reduction, you know, a mechanism which we are using. We're not using any accelerometer. You know, we could use that too, but here we are just making the GPS reading and then calculating the speed and deceleration. And based upon that, you can come up with that whether the speed is being reduced or not.
So what was the frequency of this speed? And
we used actually every second. We need every second, and within it takes only 3 to 4 seconds to make a decision whether you want to issue the trigger or not. So every second. if you do, if you want to make a decision quicker and you take the speed maybe every 200 milliseconds, what will happen is that the speed calculation, because of the error, right, within the GPS, there is an also error involved, so that won't be that accurate. And we noticed that, if you are able to do the, say, 60 miles per hour, it's about 27 meters per second, right? So within that, that's really the outside of the range of the error of the GPS. So we thought that 1 second speed calculation is much better, and then it would take only 3 to 4 seconds, because it has to be consistent calculation of deceleration and speed to make sure that you're going to issue the trigger. But this is a very good question. Yeah, I think these were the things which bothered us a lot, and we came up with this. About 3 to 4 seconds it takes. We can make decision quicker than that, if that is what in your mind is.
I have another question. So, did you, before implementing whatever you will be doing in the summer next year, did you also do kind of simulation of this thing in like some simulation?
Yeah, this simulation which I mentioned, that way we did those simulations, we did not do any simulation software. The simulation, basically we kind of got the profiles, the vehicle's profiles, GPS profiles, and we brought them in lab, and then GPS, we deceived the DSRC unit to, instead of getting the data from the GPS, pick the data point from the file, right? So that's what our simulation, kind of semi-simulation scenario. We did not use any software, or traffic sim or vSim kind of thing to evaluate our applications.
Don't you think you need a lot of data of that sort?
Sorry?
Do you not need a lot of?
Yeah, for example, if you travel maybe 2-3 kilometers, every 1 second, it's still manageable data.
Other questions?
Thanks for a great talk. Many questions, but I'll limit it to one. Have you done is there a sensitivity analysis that's been done to the effect of how accurate does the state information like velocity and everything have to be before these things start breaking down, or are they completely robust to those kind of things?
You have to have error bounds. We did not do detailed sensitivity analysis, but that's exactly the follow-up question. Basically, that's why we decided that the decision has to be made between 3 to 4 seconds, so that you are able to calculate the speed not based upon 200 millisecond apart, but rather 1 second apart, and then another second and another second, and the deceleration rather between 2 seconds apart, right? So because you have a speed here, here, and here, we thought that the speed between the 2 points which are 2 seconds apart is much better to calculate the deceleration. So and that is to ensure that the GPS accuracy was not hurting us. We have done some analysis on the GPS accuracy itself, and we thought that it was around 5 meters or so in the urban area. In the rural area, we got better. So within 5 meters or so, I think we wanted to make sure that it takes about 3 to 4 seconds, but not the detailed sensitivity that what is the actual velocity. But I think these tests, the purpose of these tests was that whether our algorithm was okay or not, right? So you can see many deceleration profiles, right? So we were able, the red line is our threshold, the standard deceleration, and each time we were able to issue the trigger when our deceleration was more than this red line, and when it was higher, it passed our algorithm test, our calculation test. So that's all what we have, not the detailed analysis yet.
And is there any, future evolutions of DSRC? Are they thinking about broadcasting other information other than just like velocity, like control inputs? Someone is pushing. Wouldn't that make things a lot easier? And is that part of the future plan? I don't know.
That is absolutely true. And as a matter of fact, the project which we are doing, we're not necessarily broadcasting the velocities. Rather, we are working on with the work zone people and the state and federal stakeholders. What is the important information which you want us to transmit in our TIM message, right? Traffic information message. This is a standard message, just like BSM, basic safety message. That is where you transmit our broadcast. Not necessarily BSM is not supposed to be for broadcasting. TIM can be broadcasted, right? So TIM can have variety of information, many optional. BSM has only the basic information, the location and the velocity and the speed and the heading, these kind of things. So I think this is definitely, the future is growing towards that, and it's a draft kind of protocol, that what should be in the TIM. So anything which is useful and which we can create, that can be part of the TIM. At this stage, it's a draft version.
Other questions? Nothing. All right. Well, thank you again, Dr. Hay, for making the drive down from Duluth. If anybody's interested in watching any of the previous seminars that we've had, feel free to log into the Roadway Safety Institute website. It's roadwaysafety.umn.edu. They're all cataloged there, and you can see previous seminars that have started. We started way back in the beginning of September. It's hard to believe that we're already in December. So thank you, everybody, for coming. If you have any questions, I know Dr. Hay will be here for just a few more minutes, and thanks again for coming.
Thank you very much for coming.